All right, these are the last two problems in AP packet number 1. But let f and g be functions given by f of x equals e to the x and g of x equals natural log of x. Find the area of the region enclosed by the graphs f and g between e to the 1, or between x equals 1/2 and x equals 1. So part A, we should graph these things. Now, let's see. Did I use a calculator? I think this could definitely be done without, but let me see. Oh yeah, I guess I did use a calculator. So, okay. Sorry. All right. So for this one, the first thing I want to do is, what's happening? There we go. The first thing I want to do is get these two functions graphed. So one of the equations is e to the x. The other is just natural log x. Those are inverses of each other. Now, what about your window? You could just do zoom 6 if you're not sure, and then zoom things in. Wait a minute. Oh, yeah, okay. And there is no intersection here, right? These are inverse functions, but we're looking between x equals 1/2. Let me change my window. X equals 1/2 to 1. So maybe I will adjust the window just so I see the portion that I'm looking at. So zoom fit. So it's something like this. It's this weird little region here. So, all right, let's sketch that graph. Now, we should have been able to sketch the graph without the calculator, right? E to the x is an exponential function. It goes through 0, 1, but we're starting here at 1/2. And then natural log of x is, let me spread this out a bit more. Natural log of x goes through 1, 0, and it does something like this. And we're looking at where, I'm really getting kind of crazy here. Okay, we're looking at where these two vertical lines enclose this region. So we're just looking at this portion here between the two graphs. All right, so the top is the e to the x, the bottom is the natural log of x. The bounds are 1/2 to 1. So this should be the integral from 1/2 to 1 of e to the x minus natural log x. Top minus bottom. Remember to put your dx in there. And I'm going to use my calculator here. So math, 9, 1/2 to 1. Now I can type in e to the x and ln x, or I do have them in y1 and y2. So you have that option as well. So I'm getting 1.223 approximately as that area. Part B, that's all we had to do for part A. Part B says find the volume of the solid generated when the region enclosed by the graphs f and g between 1/2 and 1 is revolved about the line y equals 4. So the line y equals 4 is higher than this point, right? Because this point is when you plug in 1 to e to the x, you get e. Remember, e is like 2.7182, et cetera, et cetera. So 4 is up here. So let's go ahead and sketch this graph. So again, I'm just going to kind of sketch in this region that I'm looking at, something like that. Now that goes up to E. It's going from 1/2 to 1. So 4 is like somewhere up here, right? So 4 is this line here. This is my axis of rotation. You don't have to draw the reflected thing, but it would be something like this. I just kind of like to sketch it. Oh, I think I did it wrong though. There we go. It'd be something like that. And then this is going to be a washer method, right? You're going to form this like weird kind of curved bowl on the outside, and then it'll have this scooped out center. So the outer connects the axis of rotation to the outermost part of your function. That's going to be our capital R. So what is that? Top minus bottom is 4 minus, this bottom function is natural log x. And then what's the inner portion? So connect the axis of rotation to the innermost part of your function. So like this little top curve here. And that lowercase r would be 4 minus e to the x. And we're talking about volume where we're rotating. So the volume formula is pi times the integral from 1/2 to 1. You're using all the x values just where this shaded region is bounded by. And then capital R squared would be 4 minus ln x, the quantity squared, minus lowercase r squared, 4 minus e to the x, the quantity squared, dx. And then we'll see what this comes out to. Now, half the time I forget to put this pi in if I'm just copying and pasting something, although I didn't have anything to copy paste. So just be careful of that. So pi times math 9 1/2 to 1. Parentheses 4 minus ln x squared. Hold on. Parentheses squared. I don't want to use y1 and y2 because this is technically y2, this one's y1. These are easy enough just to type in. So I only usually use y1 and y2 when the expressions are more complicated. So minus parentheses 4 minus e to the x parentheses squared dx. 23.609 is our approximation for that volume. Okay, and then what's part C? Let h be the function where h is f of x minus g of x. Okay, find the absolute minimum value of h on the closed interval 1/2 to 1, and find the absolute maximum value of h on the closed interval 1/2 to 1. Show analysis that leads to your answers. So in general, how do we find the absolute min and absolute max of something? So remember, this is that extreme value theorem where you have candidates. The possibilities for extreme or for absolute max and min are the endpoints of the interval. So that's x equals 1/2 and 1. And any relative extrema. And we're looking for both absolute max and min. So I'm looking for relative max or min as well. All right, well, how do we find relative extrema? That would be when our function's derivative is 0 or undefined. So our function is h of x equals f minus g. So that means we need to find h prime of x. So that would be f prime of x minus g prime of x. And what is f prime of x? So f of x was e to the x. So what's f prime? E to the x. That's easy. G of x was natural log of x. So what's g prime? 1 over x. So that's h prime of x. And we want to know, where is that equal to 0 or undefined? So for critical numbers, we could say h prime of x. I know it's undefined at 0, right? So h prime of x is undefined at x equals 0. Okay. And where is it equal to 0? Well, let's just type this into our calculator. Remember, we're allowed to use a calculator. So instead of solving algebraically, let's just type it in and see what happens. So let me clear these out. So I'm looking at graphing h prime. So e to the x minus 1 over x. I only want the window to be 0.5 to 1, and I'm going to zoom fit in case it's anything different. So we do hit 0 right here. And then I got the x equals 0 for my domain here. So let's see. Second trace 0. Another way to find the 0 is to graph the line y equals 0 and find the intersection. But if I'm choosing the 0 option, I've got to get my cursor to the left of the 0, press enter, and to the right, and press enter, and have it guess. Let's write down this whole thing. So split screen here. So this is when x is about 0.5671433. Let's also make note, remember the AP graders won't grade this part of our work, but what that means is we can plot this point, and let's just make note of, this is the h prime graph. So it's negative and then it's positive. So h is decreasing and then increasing. So this is a relative min location, just kind of FYI. So it's not a candidate for the maximum. It is a candidate for the minimum. All right, and actually looking at h prime, so it should be, let's see, so we're going to start at a certain value, and then h is going to decrease until it gets here, and then h increases for a much larger change in position there. So I have a feeling our maximum is going to be at the end, and our minimum is going to be at this relative minimum. We have to find the values anyway, so yeah. All right, so our candidates are endpoints and values and our relative minimum there. So h of x, remember, is f of x minus g of x. Actually, let's go ahead and write down. So e to the x minus natural log of x. All right, so our candidates, oh, and 0, by the way, is out of our range, right? We're only looking from 0.5 to 1, so that's why this didn't even really factor in. All right, so the endpoints are 1/2. I have this 0.5671433, and then I'm also going to plug in 1. So let's just do this here. So e to the 1/2 minus natural to the 1/2 minus natural log of 1/2, 2.342. And then what do I get when I do the same thing, but I'm plugging in this decimal? I get 2.330. A little bit smaller, right? We said that ought to happen. And then when I plug in 1, I don't think I need a calculator for this. E minus ln1. And remember, ln1 is 0. E is about 2.718, I think. So definitely the largest number. All right, so now you will get this little chart. This is the extreme value theorem. So this is allowed to be your evidence. And then the question was find absolute max and absolute min. So the absolute minimum is about, I'm going to say, 2.330. And the absolute maximum is, I'm not going to say about, I'm going to say E is the absolute maximum. All right, last problem. Let R be the shaded region bounded by the graph natural log x and x minus 2 as shown above. Find the area of R. So this is another, we're allowed to use a calculator for this one. Remember our quiz, I've got 3 calculator allowed for your response questions for you. All right, so natural log x and x minus 2. What about my window? I'm going to say, I don't know, we can just zoom 6 to begin. And then, yeah, this is good enough. If you want to zoom in, you can. Oh, but zooming in kind of messed me up. Let me bump my window out a little farther. Take it to 4. Okay, so I can see my 2 points of intersection here. I need to find those 2 points. And because my area is going to be top minus bottom, I want the x coordinates of those 2 intersection points. So write these down with as many decimals as you can see. And you should define them. I have been kind of sloppy about this on my actual video here. So what I should be doing is saying, if I don't want to keep writing these decimals in my work, I'm going to say, okay, A is 0.1585943. And B is the other intersection point. If I define these clearly, it's not enough to just define it on the picture and then use A and B. You do need to write it down in your workspace. When you take your AP exam, you will have little boxes for your workspace, just like our AP pre-calc test. So you'll need to write it in the box for the first problem. And this is 3.1461932. Right. And find the area of R. Now, another thing you can do, again, you don't have to do this. If you want to just type in the decimals, it's not that big of a deal. But you can store numbers on your calculator. I can say store this, that's a STO with an arrow, and then I can use the alpha and the letters. So I can say store that as A. So now when I type in A, the calculator knows it's that value. And I can do the other one as B. Again, not required. This is just if you find this convenient, then great, you can use that. So I want to, for part A, I want to find the integral from A to B of top minus bottom, which would just be ln x minus the quantity x minus 2, or distribute that through. It is wrong if you say minus x minus 2. That's not mathematically the same. So please be careful there. And then because I stored these values here, yeah, when I set up my integral, I'm going to do alpha A to alpha B. And then ln x, I'm just going to distribute here, minus x plus 2. So this is about 1.949. Okay. And you don't have to keep redefining A and B, so you can use these now throughout the problem. So part B says find the volume of the solid generated when r is rotated about the horizontal line y equals -3. So it is always a good idea to resketch when you're doing the volume ones. So, okay, here's what our original area is kind of looking like, something like that. It does not reach down to -3. You can verify that on your points of intersection if you want to, but -3 is lower. So -3 is like down here. So if we rotate this around, there is going to be some empty space. So this is the washer method. So we need this is our little axis of rotation. Then we want from the outside of our function to the axis of rotation. That's our capital R. So capital R is what's the top function there? That's ln x minus the axis of rotation, -3. So it's actually ln x plus 3. The signs do matter here. I know some of you are subtracting backwards or saying like, oh, well, it should just be like it's not going to matter if it's -3. It will matter with the math at times. So in this case, it would. Whether you have -3 or +3 will matter. Lowercase r is the inner portion. So connecting to this line back down to the axis of rotation, the line is x minus 2 minus -3. If you just always get in the habit of writing top minus bottom or right minus left and then simplifying, things will be much better. So x minus 2 plus 3 is actually just x plus 1. So now the volume is pi times the integral from A to B again, because both the inner and the outer have the same bounds. The inner doesn't start at a shorter spot than the outer. And then it's capital R squared, so ln x plus 3 is getting squared minus lowercase r squared dx. All right, so let me go back to my calculator. So pi, get this on here, math 9, A to B, because I've already stored those, parentheses, natural log x, close that out, plus 3, parentheses, squared. Minus x plus 1 squared dx, 34.199. All right, and then part C, write but do not evaluate. That's always nice to see. An integral expression that could be used to find the volume of the solid generated when r is rotated about the y-axis. So we don't have to solve this one, but we do have to write out what it would be. So here's my region that I'm starting with again, region R. If we reflect across the y-axis, it would be something like this. Oh, no, it wouldn't. Okay, hold on. It would be something like this. There we go. Again, the 3D part does not matter, but you have your axis of rotation and you're connecting the outside to the axis. So in this one, it's the line. Now, if I'm going sideways, I need the equations in terms of y. So the line started out y equals x minus 2. You need to solve that for x. So y plus 2 is equal to x. So capital R is y plus 2 minus 0. And then lowercase r is the curve to the axis of symmetry. So that one started out as y equals natural log of x. Remember, to get rid of a natural log, you base e both sides. So e to the y is equal to x. So lowercase r is e to the y minus 0. And then we don't have to solve this, but what would the bounds be? It's not a and b anymore. It's the y values. So I guess I did need the y values. I'm not going to write c and d because this is the only time I'm using them. So I'm just going to go ahead and find them and just write them down in my integral. Actually, so v equals pi times the integral of what? So let's see. Intersect. I want to find the bottom one first. Why does it matter? It doesn't. I guess it would have been more efficient for me to find that one, but whatever. Okay, so enter. So the y value is down here is negative 1.841406. Find another intersection point. So get that cursor back closer to the other side. So enter. This is 1.1461932. All right, so I've got the bounds, and then it was capital R, so this is going to be y plus 2 squared minus lowercase r, e to the y squared, dy. You don't have to rewrite this. I just want to make sure that you remember that this is e to the 2y. That's just like if you're searching for multiple choice answers, I hope you remember power to a power is to multiply. When we type this into our calculator, we don't have to simplify anything. So it's going to be pi, math 9, type these decimals out. And then parentheses, we have to write x, so x plus 2 squared minus e to the 2x. Instead of me writing e to the x in parentheses squared, I'm just going to do that. So that's 17.099. Oh, I wasn't supposed to do that. See, I just wasted time. Oh, well. Okay. I always do that. It says write but do not evaluate, and when I can evaluate, I do it anyway. So you don't get docked if you show the answer, but we didn't have to. So, oops, gosh. So that whole thing is my answer. All right, that finishes this first AP packet. This one is the longer of our two, but you hopefully are getting into getting the hang of figuring out this washer method, and the pictures are very important. So make sure that you're sketching something to get yourself started.